Hello, this is Serene from Exam Hub 5. Today I'll be solving Physics Paper 2 AS Level Structured Questions 9702 Paper 2. We're into February-March 2021. Question number 1, Part A. Complete Table 1.1 by stating whether each of the quantities is a vector or a scalar. So acceleration is a vector quantity, and power along with work, they are scalar quantities. Part B, the variation with time t of the velocity v of an object is shown in figure 1.1. Okay, so from t is equal to 0 until t is equal to 4 seconds, the object is moving with a constant acceleration, that is constant increase in gradient, followed by constant speed. This horizontal axis means constant speed from 4 seconds to 8 seconds for an interval of 4 seconds. And at last, the object starts to move with constant deceleration for the next 4 seconds, and then it comes to rest at t is equal to 12 seconds. So part 1, determine the acceleration of the object from time t is equal to 0 to time t is equal to 4 seconds. So acceleration is final velocity, which is 1.4 meters per second, minus initial velocity, which is 0.7 meters per second, divided by the time interval for this change of velocity, which is 4 seconds. So 1.4 minus 0.7 divided by 4, this is equal to 0.175 meters per second squared of acceleration in the first 4 seconds. Part 2, determine the distance moved by the object from t is equal to 0 to time t is equal to 4 seconds. So for the first 4 seconds, it covers this distance, which is area under the graph, and the area is that of trapezium, and that's half into height. Height of the trapezium is 4 seconds. Into sum of parallel sides. So sum of parallel sides are 0.7 and 1.4. So 0.7 plus 1.4, this is equals to 4.2 meters. So the object travels a distance of 4.2 meters in the first 4 seconds. Now in the next 4 seconds, this object is going to cover the area of a rectangle, which is length into breadth. So 4 into 1.4, which is equals to 5.6 meters. In the last 4 seconds, the object travels, or the object covers the area of this triangle. So half into height into base, and this is equal to 2.8 meters. So in total, the object travels a distance of 4.2 plus 5.6 plus 2.8. So this is equals to 12.6 meters of distance in the first 12 seconds. Part C1, define force. So force in terms of momentum is rate of change of momentum Part 2, the motion represented in figure 1.1 is caused by a resultant force F acting on the object. On figure 1.2, sketch the variation of F with time t is equals to 0 to t is equals to 12 seconds. Numerical values of F are not required. So resultant force, according to the formula, F is equals to m into a, is directly proportional to acceleration. For t is equals to 0 to t is equals to 4 seconds, you see that the acceleration stays constant, meaning constant gradient, so the resultant force is also going to stay the same. So for the first 4 seconds, the value for F is going to stay same. So let's mark it here. Now for t is equals to 4 seconds to t is equals to 8 seconds, when it is covering the area of this rectangle, you see that the acceleration is 0, the object is moving with a constant speed, hence the value for F must be 0 in this interval of 4 seconds. So from t is equal to 4 to t is equal to 8, this is going to be 0. The magnitude of the F is going to be 0. It will come onto the x-axis. Now for the last 4 seconds, from t is equals to 8 to t is equals to 12 seconds, the deceleration is constant. As you can see, the gradient is changing at a constant rate, so F is again going to be constant, but this time the magnitude of F will be bigger than the F for the first 4 seconds, and it will lie on the negative axis of F, because here, if you observe, the gradient is steeper, much steeper, means the magnitude of acceleration is much greater, hence the magnitude of F will be greater, and this is the negative acceleration. And since it's decelerating, this means that the force which is of bigger magnitude is in the opposite direction this time as compared to that which was in the first 4 seconds. So this makes the value of F go in the opposite direction. So for the last 4 seconds, it's going to be of much bigger magnitude, and it's going to lie in the negative axis of the graph. Now, question number 2, part A, say what is meant by work done. So work done is equals to force multiplied by distance in the direction of force. Now, part B, a beach ball is released from a balcony at the top of a tall building. The ball falls vertically from rest. So the initial velocity with which this ball moves is 0 and reaches a constant velocity. The gravitational potential energy of the ball decreases by 60 joules as it falls from the balcony to the ground. The ball hits the ground with a speed of 16 meters per second and kinetic energy of 23 joules. Part 1 showed that the mass of the ball is 0.18 kilograms. So the initial velocity of the ball is 0. The GPE, or the gravitational potential energy loss, is equals to 60 joules, and the kinetic energy kinetic energy which this ball possesses at the ground level is 23 joules, which is equal to half into the mass of the ball, which is unknown, into the final velocity with which it reaches the ground level, which is 16 meters per second square. Hence, the value for mass is equals to 0.18 kilograms. Part 2, calculate the height of the balcony above the ground. So the gravitational potential energy loss is 60 joules, which means that gravitational potential energy at the balcony level is 60 joules, which is equals to the mass of the ball multiplied by the 9.81, which is g, into the height of the balcony above the ground. Hence, the height is going to be of 34.04 meters. Part 3, determine the average resistive force acting on the ball as it falls from the balcony to the ground. So this is the resistive force, not a normal force, but a resistive force. The ball has gravitational potential energy at balcony level of 60 joules, and as you all know, that energy must be conserved. However, energy of the ball at the ground level is just 23 joules, as it is stated right here. This means that 60 minus 23 joules, which is 37 joules, was lost to the surroundings by the ball in the form of heat. So the energy lost, which is 37 joules in the form of heat, is equals to the resistive force multiplied by the distance it covers from the balcony level until the ground level, which is of height 34.04 meters. Hence, the resistive force that is experienced by the ball while it travels from the balcony to the ground level is of 1.09 newtons of magnitude. Part C, state and explain the variation, if any, in the magnitude of the acceleration of the ball in B during the time interval when the ball is moving downwards before it reaches constant terminal velocity. Okay, so as soon as the ball starts to fall, it will always fall under the influence of free fall due to gravity. So the initial acceleration of the ball is always going to be of 9.81 meters per second square, which starts to decrease over time since air resistance starts to increase as the velocity of the ball increases, which reduces the resultant force acting on the ball until that object reaches terminal velocity state where its acceleration gets 0, where no resultant force acts on the ball. So initially, this question is of 3 marks. Each mark will be credited towards 3 of your statements. So initially, the ball falls with acceleration of 9.81 meters per second square due to free fall, and then it starts to decrease because drag force or resistance, you name it. Increases with time. Which decreases resultant force acting on the ball. And since they are directly proportional, when resultant force decreases on the ball, the acceleration of the ball will eventually decrease. Question number 3, a spring is extended by a force, the variation with extension x of the force F as shown in figure 3.1. Part A, state the name of the law that relates the force and extension of the spring shown in figure 3.1. So since the gradient of the graph of force versus extension is a straight line graph through origin, we can say that it's Hooke's law. Part B, determine the spring constant of the spring. So the spring constant has a formula of force divided by extension. We can take any of the two values from the figure of 3.1. Let's say that I use the value of 4.6 newtons of weight, which causes an extension of 3.3 centimeters. So force of 4.6 causes an extension of 3.3 centimeters, so I must convert centimeters to meter, so that it becomes 0.033 meters, and hence the spring constant is of 139.4 newtons per meter. Part 2, the strain energy in the spring when the extension is 4 centimeters. So the strain energy has a formula of half into force into extension. When the extension is of 4 centimeters, the force that is being exerted on the spring is going to be of 5.6 newtons. So 5.6 newtons of weight, which causes 4 centimeters of extension. I must convert centimeters to meters. The spring possesses a strain energy of 0.112 joules. Part C, one end of the spring is attached to a fixed point. A cylinder that is submerged in a liquid is now suspended from the other end of the spring as shown in figure 3.2. The cylinder has length 5.8 centimeters, cross-sectional area of 1.2 into 10 to the power of negative 3 meters squared, and weight 6.2 newtons that acts from the center and it acts downwards. So I must label it just to make things clear and easier. The cylinder is in equilibrium state. So all the forces that are acting on the cylinder must be equal when the extension of the spring is 4 centimeters. So when the extension of the spring is 4 centimeters, this is found in the state of equilibrium. Part 1 shows that the upthrust acting on the cylinder is 0.6 newtons. So the cylinder is in equilibrium state, so all the forces must be balanced that are acting on the cylinder. Its weight that acts downwards must be equal to all the forces that are going to act upwards. And one of those two forces is the force due to the spring, which acts upwards, and the other one is the upthrust. So we can write that weight, which acts downwards, is equals to upthrust plus force due to spring. Weight at any time is going to stay constant, and that's 6.2 newtons is equals to the upthrust, which is unknown, and that's what we have to determine, plus force due to spring when the extension is 4 centimeters, because that's when the cylinder is found in the state of equilibrium. So when the extension of the spring is 4 centimeters, the force that's being exerted on the spring is 5.6 newtons. So 5.6 newtons of force acts upwards. Hence the upthrust is equal to 6.2 minus 5.6, and that's equal to 0.6 newtons. Part 2, calculate the difference in pressure between the bottom face and the top face of the cylinder. So always and always remember, upthrust is only due to difference in pressure between the bottom face and the top face of cylinder. So difference in pressure is equals to upthrust that acts on the cylinder, which is 0.6 newtons, divided by the cross-sectional area of the cylinder, which is 1.2 into 10 to the power of negative 3. And that gives us the total difference in pressure as 500 pascals. Part 3, calculate the density of the liquid. So pressure due to liquid is equals to density into G into H. So density is going to be equal to pressure due to liquid from the last part, which is 500 divided by 9.81. And the height of the cylinder is the length of the cylinder, which is 5.8 centimeters. We need to convert that to meters. So 5.8 divided by 100 to convert centimeters to meters, and hence the density of the liquid is about 878.8 kilograms per meter cube. Part D, the liquid in part C is replaced by another liquid of greater density. State the effect of any of this change on the upthrust acting on the cylinder. So greater density means a greater difference in pressure, because pressure is directly proportional to density. So when the density increases, pressure, there will be a greater difference in pressure on the top and at the bottom, which in turn means a greater upthrust, because those two quantities are again directly proportional to each other. So the upthrust is going to increase. Now, part 2, state the effect of any of this change on the extension of the spring. Greater density means upthrust increases, and when upthrust increases, when the cylinder is in the state of equilibrium, its weight is equals to upthrust plus force due to spring, which is equals to force due to spring, which is directly proportional to, and this force due to spring is directly proportional to the extension of the spring. Now, when the upthrust increases and weight stays constant, this force due to spring is going to decrease. And when this force due to spring decreases, which is directly proportional to extension, eventually the extension of the spring will decrease too. So the extension decreases. Question number 4, part A, state the principle of superposition. So this is when two waves overlap, resultant displacement is the sum of the individual displacements. Part B, a transmitter produces microwaves that travel in air towards a metal plate, as shown in figure 4.1. The microwaves have a wavelength of 0.04 meters. A stationary wave is formed between the transmitter and the plate. Part 1, explain the function of the metal plate. So this metal plate is being used to, now this transmitter is transmitting waves, microwaves, and this is being used as a reflector, so that when it reflects waves, and then only a stationary wave will form. To form a stationary wave, you must have reflected rays too. So to reflect the waves, we have this metal plate being placed in this experiment. So this is being used as a reflector. Part 2, calculate the frequency in gigahertz of the microwaves. So the speed of any of the electromagnetic waves is 3 into 10 to the power of 8 meters per second. And especially this microwave has a wavelength of 0.04 meters. Hence, the frequency is going to be equal to 3 into 10 to the power of 8 divided by 0.04. And this is equals to 7.5 into 10 to the power of 9 hertz. We need to give our answer in gigahertz, so we'll divide it by 10 to the power of 9. So this will become 7.5 gigahertz of the microwaves. Part 3, a microwave receiver is initially placed at position X, where it detects an intensity minimum. The receiver is then slowly moved away from the X directly towards the plate. Determine the shortest distance from X of the receiver when it detects another intensity minimum. Okay, suppose this is the column where the stationary wave will form, where the right hand side is the metal plate. Suppose this is the metal plate. And somewhere here is position X, where I have placed this microwave receiver. Suppose that when receiver was at X, the wave pattern that forms is going to be like this. Suppose, just suppose, okay? We're not sure whether this form of wave pattern forms or not. Okay, so this is an open end and a closed end thing. This column has an open end and a closed end, so there's going to be an antinode on the open end and a node on the closed end. Now this will change to this waveform when the transmitter, when your question says that the transmitter is being moved away from X, position X, and it is being moved towards metal plate. So the next wave pattern that forms, and it makes the next minimum possible, is when this wave pattern changes to this one. So again, this is the metal plate, and here your microwave receiver is being placed, and X position is somewhere here, and the microwave receiver was moved away from X and it was moved towards metal plate. Now the distance from X to metal plate, which is the length of this air column, is a fixed distance, and that is 5/4 of lambda. And the distance from here, when microwave receiver was moved away from position X and it was moved here, the length of the column, which is also the distance this waveform covers, is again fixed, and it is equals to 3/4 of lambda. And the question has asked you to find this distance, which shortly we'll be determining. So 5/4 of lambda is this distance, and 3/4 of lambda is this distance. So we can calculate this d by subtracting this distance from this distance. So 5/4 of lambda, where lambda is equals to 0.04 meters. So 5/4 of lambda, which is 0.04 meters, minus 3/4 of lambda, which is 0.04 meters, and hence the distance from X of the receiver when it detects another intensity minimum is going to be equal to 0.02 meters. Part 2, determine the number of intensity maxima that are detected by the receiver as it moves from X to a position that is 9.1 centimeters away from X. Okay, so the next part is asking you to, let's suppose that this is position X, this is position X, and now there is a distance of 9.1 centimeters from position X to the microwave receiver that's being put here. So this is the microwave receiver that's put here, and this is the distance that has already been given to you, 9.1 centimeters. Now you have to find how many number of intensity maxima were received or were detected by this receiver. So from position X until this position, we know that some waveform will form, and the lambda is of 4 centimeters. This means that in this gap from here until here, 2 complete cycles, because 9.1, if you divide 9.1 by 4 centimeters, that gives you something greater than 2. So 2 complete waves, and some extra can fit in there, but that extra will not be exactly half, because this is not equal to, because 9.1 divided by 4 is not going to be equal to 2.5, but it's going to be in fact less than 2.5 but greater than 2, somewhere between 2.275 or 2.28. So we're going to have 2 complete wavelengths, one complete wave, another complete wave, and another wave that's going to be much less than half of the wavelength. So these 2 waves and some extra. So and a maximum intensity is going to be all the points that are on the highest amplitude. So 1, 2, 3, 4, and 5. So there are going to be 5 points where the amplitudes are going to be the highest. So we can say that the number of intensity maxima that are going to be recorded by the receiver, they're going to be 5. Question number 5, a source of sound is attached to a rope and then swung at a constant speed in a horizontal circle. The source moves with a speed of 12 meters per second and emits sound of frequency 951 hertz. The speed of sound in air is 330 meters per second. An observer standing at a very long distance away from the source hears the sound. Calculate the minimum frequency to 3 significant figures of the sound heard by the observer. So the minimum observed frequency is going to be heard by this observer when the source of sound is somewhere here, far from the observer. So the observed frequency has a formula: frequency of source multiplied by the speed of sound in air divided by speed of sound in air plus and minus depending upon whether it's going to be hearing the minimum frequency or the maximum frequency, plus or minus the speed of source. Okay, so observed frequency is going to be equal to 951 into 330 divided by, if it's the minimum frequency, then 330 plus 12. The question we're asking you to find the maximum frequency, it would have been 330 minus 12. This time is 330 plus 12 since it's the minimum frequency, and so this is equals to 917.6 hertz. And since the question is asking you to round it to 3 significant figures, we'll make it 918 hertz. Part B, the circular path of the source has a radius of 2.4 meters. Determine the shortest time interval between the observer hearing sound of minimum frequency and the observer hearing sound of maximum frequency. So this is the point where the observer will be hearing a minimum frequency, and this is the possible point where it here's where this observer will hear a maximum frequency. So the distance between the minimum frequency point and the maximum frequency point is going to be half the circumference of the circle being covered. Now the circular path that it travels has a radius of 2.4 meters. So the distance in total it covers is going to be equal to 2 pi r, and r is 2.4 meters. So in total it covers a distance of 2 into 2.4 pi meters. So the distance between the point of minimum frequency and the point of maximum frequency is going to be half of that. So distance is equals to 2.4 pi meters. And the speed with which this object is moving is 12 meters per second. Now the time interval is going to be 2.4 pi divided by 12. So this is going to be equals to 0.63 seconds. Question number 6, part A, state Kirchhoff's first law. So this states that sum of currents entering a loop is equal to sum of currents leaving that loop. Part B, a battery of EMF 12 volts and internal resistance R is connected to a filament lamp and a resistor as shown in figure 6.1. The current in the battery is 3.6 amperes and the current in the resistor is 2.1 amperes. The IV characteristic for the lamp is shown in figure 6.2. Part 1, determine the resistance of the lamp in figure 6.1. So resistance is going to be equal to voltage divided by current. So when the current in the resistor is 2.1 amperes, this means that current across the lamp is going to be equal to difference between 3.6 and 2.1, which is equals to 1.5 amperes. Now 1.5 amperes of current across the lamp means that 4.4 volts of PD is across lamp. So 4.4 PD and 1.5 amperes of current, this is equals to 2.93 ohms. Part 2, determine the internal resistance R of the battery. Okay, so this is what they're asking you to calculate. When current across the resistor is 2.1 amperes, the voltage across the lamp is 4.4 volts. Which means that 4.4 volts is across the resistor too. You all must know that Kirchhoff's second law comes in here, that EMF, which is 12 volts, is going to be equal to the PD across the battery, which is 4.4 volts, plus the lost volts due to internal resistance of the battery, which is R. So lost volts are 7.6 volts. Now to calculate the value of small r, this is going to be equal to 7.6 divided by the current that flows across resistance R, and it is going to be 3.6 amperes since that's the current that flows across the whole loop. So 7.6 divided by 3.6, this is equals to 2.11 ohms. Part 3, the initial energy stored in the battery is 470 kilojoules. So this is equal to 470,000 joules of energy that's stored at time t is equal to 0 in the battery. Assume that the EMF and the current in the battery do not change with time. Calculate the time taken for the energy stored in the battery to become 240 kilojoules of energy. Okay, so to release 470,000 minus 240,000, which is equals to 230,000 joules of energy. What's the time taken? So energy released is equals to I into V into time interval. So that the energy that's being released is 230,000 divided by the current in the battery, which is 3.6 amperes, and the EMF of the battery is 12 volts. So 3.6 into 12 volts. This gives us the time of 5324 seconds. Part 4. The filament wire of the lamp is connected in series with the adjacent copper connecting wire of the circuit as illustrated in figure 6.3. Some data for the filament wire and the adjacent copper connecting wire are given in table 6.1. Calculate the ratio of average drift speed of free electrons in filament wire and average drift speed of free electrons in copper wire. So according to the formula, current is equals to NAVE. The average drift speed of free electrons is inversely proportional to the product of the number density of free electrons and cross-sectional area. Now it says that the cross-sectional area of copper wire is 360 times greater than that of filament wire. So when area increases by 360 times, the average drift speed of free electrons will decrease by 360 times since they are inversely proportional to each other. And when the number density of free electrons of copper wire increases by 2.5 times, the average drift speed will again decrease by 2.5. So in total, the average drift speed of free electrons of copper wire will in total decrease by 900 times because 2.5 into 360. Mind that it's the area factor that's increasing here, that is 360, not the radius factor. If it were radius factor that was increasing by 360 times, the average drift speed of free electrons must have decreased by 360 into 360 means the square of 360. But here, since this is the cross-sectional area that's increasing by 360, the average drift speed of free electrons will decrease by only 360 times. So the average drift speed of free electrons in filament wire is V, and the average drift speed of free electrons in copper wire decreases by 900 times. So this is going to be equal to VF by 900. So VF divided by VF by 900, this is going to be a ratio of 900. Question number 7, part A. The results of the alpha particle scattering ring experiment provide evidence for the structure of the atom. So it provides the evidence for the structure of an atom. Result 1, the vast majority of the alpha particles pass straight through the metal foil or are deviated by small angles. And result 2 is that a very small minority of alpha particles is scattered through angles greater than 90 degrees. State what may be inferred from result 1. So here it is said that majority of alpha particles are uninterrupted and they pass straight, which means that most of the atom is empty space. So most atom is empty space. And when they say that they are deviated by small angles, it means most of them are being reflected back, which suggests that just like alpha particles carry positive charge, the nucleus of the atom is also going to carry a positive charge. So nucleus is positively charged. Now result 2. Result 2 says that a very small minority of alpha particles is scattered through angles greater than 90 degrees, means they are being deflected. So this part suggests that nucleus is dense and is positively charged. Part B, a radioactive decay sequence contains 4 nuclei, P, Q, R, and S. Nucleus S is an isotope of nucleus P, means, okay, so S is going to have the same number of proton. So S is going to have same proton number, so it's going to be 84 here. Determine the proton number and the nucleon number of nucleus S. So the proton number is going to be 84. And when you notice that to convert P to Q, there is a decrease of 2 from here and 4 from here, means it is releasing an alpha particle. Now 82 to 83 and 240 remains the same. This means that it released a beta minus particle, which was 0 here and -1 here. Now from R to S, again an increase of 84, which means again a release of beta minus particle. This means that 214 will stay the same right here. So the nucleon number is 214 here. Part 2, the quark composition of a nucleon in Q changes as Q decays to form R. Q to R is a release of beta minus particle. This means that a neutron will change to proton and a down quark will change to an up quark. So beta minus decay, which means a neutron turns to proton and a down quark changes to an up quark. So that was the end of the video. Thank you for watching.